Hello everyone, this is Dr. Ali, and in this session we continue where we stopped last session, that we were explaining about this knapsack problem, and we saw the code for using evolutionary algorithm using this package sci-fi.optimize differential evolution, which this differential evolution is one of the many algorithms that are coming for this evolutionary algorithms. Then we see that when we run here, and for this specific example, it gives us the sequence here. 0 means that don't pick the first item, select the second item, ignore the third item, index the item in the third index, and so on. And the maximum value that we obtain from with this sequence is 120, and its weight is 8, which we see is not surpassing this maximum weight of the knapsack. Now, let's focus on this chart. And what is this chart? It is the value versus weight. Okay, so this is kind of very popular way to see that how this evolutionary algorithms are working. And remember that kind of we had two objectives. Well, to be quite accurate, if we look at the how we started, we had an objective function and we constraint, right? But the thing is, you can also consider this objective function as a one goal for maximizing, and this constraint is considered as another objective function that we want to minimize. This is just something that kind of for the intuition that you need to understand this chart that I'm about to explain. Because to me, I also consider this constraint as an extra object that we want to minimize. That's why we also were able to kind of add them together, because this was an objective, this was a constraint, but we normalized it and we added together. So we add the constraint to the objective function. So we can say that both of them we have two objectives. That one is we want to maximize, the other one we want to minimize. So what I'm saying is we want to maximize the value, correct? We want to, as much as we can, pick and put it in the knapsack. So the more we go to the right is the better for this method. But weights, we want to be as small as possible because we want to pick more. So if the weight that items that we picked is smaller, this is better for us. So weights wanted to go down, values want to go right. So this forms this Pareto frontier that all of these dots that are the different value weight value weight combinations, that during all of these iterations that I mentioned that happens in differential evolution happens, it will generate different or evaluate different combination with its own associated value and weight. For example, if let's say this sequence, right? This is one of those many sequences that this algorithm tried. This one has a weight 120, value 120 and weight 8, which is this red dot. So I assume there are lots of other of these combinations that this algorithm tried, and these ones are showed with these black dots. But what I'm saying here is all of these points that you see are in the front. These points, these are known as Pareto frontier. This is very common in these multi-objective problems, that there is no one solution. There could be many solutions based on the consideration. So, for example, this dot here, right? You cannot say this dot here is worse than this dot here. Why? Because if you look at this dot, its value is less, right? So it means that this dot, whatever combination leads to this value, is worse than this dot here. But if you look at the weight objective, this guy has the less weight. So from weight perspective, this point is better than this point. But from the value perspective, this point is better. So you see, depends on what it is that we want to look at. So then we actually consider that as the best. But here, because we wanted to maximize the actual value, so we wanted to, this would be as, toward the right as possible. So we picked this one because we wanted to focus on the value. So this is the part4 frontier. So let me actually, and this code was corresponding to the first method that I explained, that actually the second method. Remember, I said there are two ways that I can turn this, maximize this equation that we had to actually minimization formula, right? So this was the first method that I'm using, minus times this equation. The second method was reformulating everything based on the those value of items that we didn't pick. This one we already see. This implementation was related to this form that I explained. But now let's look at this, the first method, just to say, for clarification, to showing you these two should lead to this very similar solution. So let me comment this out and uncomment. This part that I uncommented is basically implementation of this method. So if you look at the this formula, it says there is a penalty, which actually in line 24. Let me pull up this slide one more time. Okay, so we have this penalty which says alpha times this equation, which is the same as before. But the only part that is missing or changing is that for the cost function, we have minus alpha minus 1 times total value plus penalty. Total value we calculated times penalty. So that's the actual only part that is different. So if I run this, so you see, we reach the same number, 120 with the optimal weight 8. So if I run the, you see, it gives us different set of points, but still it reached the same value that we reached at the first method. This is not the general rule that these two always would be the same, but they give us, both of them are able to give us the good solution. I mean, the solution that not violating the constraint, and as at the same time give us the good value, that the maximum value that we can fit in the actual knapsack. So that's it for today. Next session we try to explain how can we solve this problem using recursion and dynamic programming. So stay tuned for the next session and have a great day, everyone.